Welcome to Chapter 7, Part 4. In this section, we're going to cover our last two of our four mechanisms. We're going to look at the SN1 and E1 reactions, or mechanisms. SN1 is going to be a nucleophilic substitution. All right, that's the S and the N. And then the 1 indicates unimolecular. Remember, the 2 was bimolecular. E1 is going to be a unimolecular elimination. Elimination, unimolecular. Now, what does this mean? SN2 and E2 were concerted mechanisms, right? The bonds broke and the bonds formed at the same time, right? Nucleophilic attack plus loss of leaving group, or proton transfer plus loss of leaving group. So in this case, both of these are stepwise. The steps of the mechanism take place separately, and it results in a unimolecular rate law. So only one of the molecules is actually important to the rate of the reaction. So let's look at this example that's shown here. When we have this tertiary alkyl halide and we are going to treat it with an alcohol, so we're seeing ethanol here, which is not strong. It's not a strong nucleophile or a strong base. It's weak. But we do get some substitution product, right, where we switch out that OET for the bromine, as well as some elimination product. All right, and we do get a mixture of them, and we're going to talk about that. We know that this can't undergo SN2 because it's a tertiary alkyl halide. We also know that that reagent is weak. It's not a strong base. It's not a strong nucleophile. So E2 and SN2 are not likely. When we look at experimental data, we also find out that it is a first-order rate law and it only relies on the substrate. So as long as there is ethanol present, the rate is only affected by the concentration of the substrate. And when we look at the mechanism, we'll understand why. So the rate determining step for both SN1 and E1 is the same. The first step is the same. That's why we look at these together. And it is a loss of a leaving group. But you notice there's no nucleophilic attack happening. There is no proton transfer happening. The leaving group leaves on its own. So we wind up with a carbocation intermediate. So this is a little bit different than a transition state. It's got a charge, so of course it's going to be less stable than the starting material or the neutral products, but the bonds are not in the middle of breaking and forming, so it is more stable than a transition state. Now from here, you can go on to substitution and elimination, but this first step is the rate determining step, and notice only one molecule is involved, right? That's where you get the SN1 and E1 identifiers. All right, so let's continue forward. If we want to look specifically at the SN1 mechanism, and then we'll look at the E1 mechanism. The SN1 mechanism starts off, or the difference is, once you have your carbocation, now that is a much stronger electrophile. So this is our ethanol. Where ethanol is not a strong nucleophile and won't attack the carbon in an alkyl halide, it will attack a carbocation. And now that it's a carbocation, it doesn't matter that it was tertiary. That carbocation is flat. It's trigonal planar. So we don't have to worry about the sterics. So we get our nucleophilic attack, And something we want to pay attention to, that proton on the alcohol is still there. We can't just get rid of it without saying how, right? A mechanism shows all the bonds breaking and forming. So there is a third step in an SN1 reaction frequently, and that is the removal of that proton. Now, there is no strong base here. If there was a strong base here, we'd be getting an E2 reaction. So to show the deprotonation, you only want to work with what's available. And we do have ethanol. So ethanol can act as our base, right? And so it'll pick up that proton. It will return those electrons to the oxygen. And we will have a neutral substitution product. Frequently, the SN1 reaction does take 3 steps, or mechanism does take 3 steps. You have the loss of the leaving group, followed by the nucleophilic attack, and finally a proton transfer to get your neutral substitution product. The SN1 and E1 reactions are often called solvolysis. The ethanol is acting as the reagent and the solvent. Look at this diagram of the reaction. Now, instead of just starting material to products and one activation energy, you have a multiple minimas and maximas. Anytime, the more steps you have, the more bumps in this reaction coordinate you're going to see. So you have the rate determining step, which is, of course, going to be the largest activation energy, right? That's the slowest step. That is going to be as the bromine is breaking. Once the bromine has broken off, you get your carbocation intermediate. The nucleophilic attack, right? It's a much smaller activation energy there. And that transition state is going to be the CO bond forming. Once that finishes, this is very slightly higher in energy, the protonated version. You do have that one last proton transfer. It's a small blip, but it is another transition state. It is another energy maximum. Local maxima, but still a maximum. So every step in the mechanism will make this diagram a little bit more interesting. Okay. We've talked about the kinetics here, right? Nucleophilic substitution, unimolecular, and the details. Now, the details, I don't know why they're showing you the generic version after showing you an example, but it does follow loss of leaving group, nucleophilic attack, and then proton transfer if needed. Now, there will be times where it's not needed. You have to evaluate. Is the nucleophile water or an alcohol? If the answer is yes, you will need that proton transfer. Then moving on to the E1 mechanism. All right, sorry for the blip in the middle of this video. I had to feed the dogs. But the E1 mechanism, let's take a look. We know that the first step is going to be the same as the SN2 mechanism. We are going to get that loss of a leaving group with a carbocation intermediate. But instead of a nucleophilic attack, now our ethanol is going to be acting as a base. Ethanol is weak. It's not a strong nucleophile or base, but it is a nucleophile and a base. So if you make that more reactive carbocation intermediate, both things can occur. So it can deprotonate the beta position and form our alkene product. It follows unimolecular kinetics, so same as SN1. As long as ethanol is present, the rate is determined by the concentration of the substrate. Now, we know the SN1 mechanism will frequently have a third deprotonation step, but if we just pay attention to these 2 steps, right? We have the loss of leaving group followed by either nucleophilic attack or proton transfer, you are going to see that first step overlaps, right? So they're both going to occur. Then, that first step will occur and you just see that one smooth line because the first step's the same. Then the second step, whether it is deprotonating or nucleophilic attack, will be a little bit different. They're often close, so in many of the examples that you will see, when you have a weak nucleophile, weak base, and you can get substitution and elimination products, you will just predict both. Now, things that can happen in the SN1 and E1 mechanisms. We need to talk about stereochemistry and regioselectivity, but we also need to talk about rearrangements. Rearrangements can only occur in these two mechanisms because you need that carbocation intermediate. Because of the concerted nature of SN2 and E2, this is not an issue. But when we have certain carbocations, if they can rearrange to form a more stable intermediate, they will. So look at this example. We lose our leaving group and we form a secondary carbocation. That leads to this product here. However, we get a significant amount of this product where the OH is adding to the carbon that looks like the beta carbon. And that is because a simple hydride shift will lead us to a more stable tertiary carbocation. You will not get a rearrangement to make something less stable, but rearrangements are very fast, and if it can make something more stable, it will. Then the water, which is our weak nucleophile, can attack, and we would get our water adding to that position. Then you would follow it with the proton transfer, right? The water will come in and pick up that proton, and you'll be left with your neutral, but albeit rearranged substitution product. Now it says also you get elimination products. In this case, the elimination products would be the same for either the secondary or the tertiary intermediate. So that's why they don't focus on that here. Something that I just want to warn you that you may see would be this concerted process of the rearrangement happening at the same time as the leaving group. I don't care if you show it in one step or two there, as long as you're not showing the reagent involved, right? It's still unimolecular. The reason that they're showing it as a concerted step in this problem is because the primary carbocation is so unstable. So the reason that this leaving group is able to leave is because it also is rearranging. You may also notice that these are called solvolysis reactions because your reagent is also your solvent. Now, thinking about the solvent, right? We know that the SN2 reaction prefers or goes faster in a polar aprotic solvent. And we see that here in this chart, this discussion. Why does that work better? Well, because you are not going to be solvating that nucleophile in as much, and so it's more free to attack. So we want to take a couple of notes here, because the SN1 and E1 reactions go faster or prefer a protic solvent, which is good because the reagent is also a protic solvent in many of these cases. So I want you to note from this chart, first of all, fluorine is not a great leaving group. So the relative rate of reaction in methanol or DMF, we're not going to worry about DMF, but in methanol is negligible. So I want you to forget about fluoride at the moment. It's not a great leaving group if you want to start with an alkyl fluoride, you usually have to throw some other tricks at it to make it work. So we're going to concentrate on iodine, bromine, and chlorine. Now you notice iodine will go the fastest in an aprotic solvent. I'm sorry, in a protic solvent. And that's because it is the most polarizable. When we think about what's a good leaving group, iodine is the best leaving group because it is bigger, right? It is going to be more polarizable, meaning that charge can spread out. So this is typically the most stable of the leaving groups. The rates of reactions go faster for SN1 and E1 in protic solvents because when that leaving group breaks off and you have a carbocation and a halide ion, protic solvents like water, like alcohol, can help stabilize the charge as well because they can surround them with all those little protons and form like a strong, it's not quite a hydrogen bond, but it's like a hydrogen ion bond. And so you notice it's much faster if you have this as your leaving group. Now, to compare that to the SN2 reaction, look what happens when we put this in DMF, right? There's a polar aprotic solvent. Everything goes much faster. The iodine isn't the fastest one anymore, but the rate is still much faster than in a protic solvent. So remember, this is for SN2 here. The DMF is not going to solvate as well, and so your nucleophile will be able to attack faster. It's not going to, but also SN2 isn't going to create carbocation anyway. So these are the notes to take away from this slightly disjointed moment in the section. SN2 prefers polar aprotic. SN1 prefers protic solvents. So overall, for SN2, the aprotic solvent is best because the reagents are already higher in energy, so it has a much smaller activation energy. For SN1, the protic solvents just brings everything down. And so it's different reasoning, but has to do with the kinetics of the reaction. This is a good note to make sure that you know. Now, as we saw in that previous chart, much more reactive are going to be the chlorine, the bromine, and the iodine. Fluorine is difficult because it is not a great leaving group, right? And we know fluoride, the big difference between fluorine and the other halogens is HF is not a strong acid, but HCl, HBr, and HI are. There are other things that can help to stabilize your intermediate. So even though primary carbocations aren't particularly stable, if they are resonance stabilized, that can be very helpful. And that can create a faster reaction rate. So even though this position right here, it's called the benzylic position, even though that's primary, it is a lot more stable than you would think for a normal primary carbocation, because that charge is resonance stabilized. Same with the allylic position. And so, let's see. Here's just an example of another substrate that could undergo SN1 and E1. You notice that the water can substitute for the bromine. It can also eliminate. Now, when it comes to E1, and we're going to talk about elimination products here. E1 does favor Zaitsev. We aren't going to see anything that favors Hoffman except that bulky base in the E2 reaction. It favors Zaitsev. Now, in this example, there is no Zaitsev versus Hoffman. one of the most common mistakes people will make here is to try to put 5 bonds on carbon. But something to note in this starting material, this is the only place with a beta hydrogen. The carbon on the left of the bromine does not have any hydrogen. So you can't eliminate to that side. So that is why you only get this one elimination product here, and it's not a major or minor, it's just only. It's the only one. However, sometimes you are going to have a choice, and so you want to favor Zaitsev. So for instance, in this example, you are going to, if I asked you for the major products, what I would want to see is the major elimination product, the Zaitsev product, as well as the SN1 product. So this one would be minor. If you were asked to draw all of the products, you would put in both. But if you're asked for the major product, we want the Zaitsev product. And this is going to be the case because, one, most of your weak bases are small, and then your Zaitsev product is more stable, right, than your Hoffman product. You can get a mixture, right, depending on where your beta hydrogens are. You can get trans versus cis, you can get Zaitsev versus Hoffman, but the major product's going to be the most stable. So trans is more stable than cis, Zaitsev is more stable than Hoffman, so this is the product I would expect you to predict for E1, and then also a mixture with the SN1. As far as SN1 goes, we know with SN2 there's inversion of stereochemistry. So with SN1, you get a mixture of stereochemistry. So if you have a chiral center, instead of getting just inversion or just retention of stereochemistry, you get both. So I'm going to draw a slightly different version of this. Let's say that we have this secondary alkyl halide. We are treating it with whatever our weak nucleophile is. Let's just say it's water. We are going to get both retention of stereochemistry and inversion of stereochemistry, right? It's a mixture. We like to say that it's a racemic mixture, but that's not quite right, and we'll talk about why. But you do get significant amounts of retention and inversion of that stereochemistry. The nucleophile can attack from the back. It can attack from the front because the carbocation is flat, right? My handwriting is terrible. Flat. There we go. With SN2, it has to attack from the back because the leaving group is in the way. You do get a slight favoring for inversion because when the leaving group leaves, it doesn't disappear, right? The bromine still exists. It's still just a big old pile of electrons, electron density, and so it will repel that nucleophile a little bit. Now, they put an X. They shouldn't put an X. It still happens. They're just saying it's a little bit less than 50%. So instead of getting a purely racemic mixture at the end, you do have a little bit of a favoring for the inversion product, right? But SN1 gives you a mixture. So we are going to, in the next, I think, let me double check. Okay. In the next video, we're going to go through steps for predicting a product, just starting with the substrate and the reagent and the solvent if possible. I highly recommend you take a look at the charts on eCampus in your extra practice folder. it will be a helpful guide as you are starting to navigate solving these problems. I will also post another video this week of me just working through problems. So once you get past part 4 in the lecture, now you can really start practicing predicting products and predicting mechanisms.